Today, we want to combine the things that we looked at this week. We want to combine vector fields and parameterized curves. So we talked about parameterized curves, which are one-dimensional curves in space, and we parameterize them specifically as vectors. We want to start describing one-dimensional curves as vector-valued functions. Then the next thing that we looked at were vector fields, where we take every point in a space and we assign a vector, and they could be pointing in all different directions. What we want to do now is combine those two things. The parameterized curve, which we could think of as the path of a bird as it flies through the air, and we want to think of the vector field as the wind blowing in all different directions at different points where the bird is flying. So here's how we're going to combine those two things. We're going to make a line integral of a vector field along an oriented curve. So we're integrating the vector field along a curve. So our vector field is a bunch of vectors, and integration is multiplication. So we have to decide on what kind of multiplication we're going to use. Looks like we're using a dot product because that's one of the kinds of vector multiplication that we have. So dot product. So if I'm going to make a dot product, I need a vector dot another vector. And the other vector is this dr. In the grand tradition of integration, what we're going to do is assume that the function, in this case the vector field, is constant for a small change along the curve. And the dr is going to be the small change along the curve. So here we're making a dot product of a vector field, the vector from the vector field, and a vector indicating the direction along the curve. Any questions? So we're integrating a vector field along a curve. Let's look at a quick example. I think I'm going to pick an example with a constant vector field, because we know that multiplication still works, or integration still works, even if one of our factors is constant. So let's consider the vector field we're going to have a constant vector field. So how about negative 1i plus 2j. And the oriented curve let's make a curve of two line segments. Let's see, 1, 1 to, let's say, 10, 1 to the point I need a point, and I drew a blank. 10, 10. I know I shouldn't have to like think so much to come up with another point. I actually had to look up and steal one because I could not think of a point that was directly above 10, 1. So I don't know if this is a too much coffee problem or a not enough coffee problem. All right, so notice that the curve, I'm saying it starts off at 1, 1, goes to 10, 1, and then goes to 10, 10. So there's a direction on the curve. This is an oriented curve. It has a direction. So just when we talk about an oriented curve, that just means that there's a start and a finish. So let's draw a picture of what's going on. The curve goes from 1, 1 to 10, 1. So I'm going to start off at the point 1, 1, goes to the point 10, 1, and then goes up to the point 10, 10. So here's the point 1, 1, here's the point 10, 1, and here's the point 10, 10. And we went from 1, 1 to 10, 1, so we're going in this direction. Here's a little arrow to indicate the direction. And then it goes from 10, 1 up to 10, 10. So we'll label the orientation of the curve. Now what we're going to do is we're going to superimpose the vector field that's sitting on top of that, in which the vector field that the curve is sitting in. Now the vector field at all points is minus I plus 2j. So the vector field is always going at a minus 1 plus 2. So there's all these slopes of negative 2 everywhere. So at every point, in the entire space, so the way we could think of this, if we use our analogy, we've got the wind all blowing in the same direction, blowing at this slope of negative 2. So blowing in the direction of minus I plus 2j. And then we can think of the curve as a bird flying from the point 1, 1. Looks like it's flying into the wind up to 10, 1. And then it's flying with the wind from 10, 1 to 10, 10. So here's our F vector field. And then down here is our curve C. Any questions? What we're going to do is our integration thing. At every point along the curve, these are all the values that we're plugging into the vector field. At every point along the curve, we're going to evaluate the vector field and find the dot product of dr. And dr is just going to be a small piece of the curve where we assume everything is going in one direction. So dr is a small piece of the curve because that's what we do in integration. This is a small piece . Now, in this case, everything is nice and flat and constant, because we're just trying to start off with something nice and simple. So at this point 1, 1, dr is going to be a small vector going in the direction of C. And we're going to find the dot product of the vector field F and this direction dr. And then when we get to the points 2, 1, let's say, we're going to find the dot product of the vector F and this small piece of the curve C. And then we're going to do that all the way along this first part of the curve. Then we're going to make our turn. Our bird is going to turn, and it's going to turn with the wind. So now I'm going to calculate at, say, 10, 2. I'm going to find the dot product of the vector field, negative 1, 2, and a small piece of the vector, a small section of the curve dr following along that direction. Any questions? We can think of this, a good example that we use a lot in this kind of setup. We could think of the integral as the work done by the bird to fly along this path in this vector field against the wind and then with the wind. So it's going to be like, oh, this is hard work, and then it becomes easier. Any questions? So at each point along the curve C, we find the dot product of the vector field F and a vector in the direction of the curve C. And then we go along to the next point on the curve, well, a point that's nearby, and we find the dot product of the vector field and whatever direction the curve is going at that point. So here, everything was nice and flat, and the vector field was all going in the same direction. The next step would be to have a curve going in some different direction. So I'd look at this point, and we have the vector field going in -1, 2, and then the curve may be going at 1, 1. Then at that point, we would pick another point on the curve and say the vector field is going -1, 2, but now the curve is going 1, 0 for a direction. And then maybe after that, the vector field is going -1, 2, and the vector field and the curve is going 1, -2. And we're just going to add up all those dot products as we go along. So the core calculation we're making is a dot product of vectors. So anything that can be calculated with a dot product is something that we can calculate with these line integrals. Any questions? All right, let's pause the video here and think about this.